There we go. Okay, so this is where we left off last time. We're going to make an array bag. Specifically, we're going to first talk about the index bag. But the idea here is just we've got a bag, and we're going to use the array to hold on to the information. We're going to keep track of the rear of the bag. And that's really it for the fields. Things that we're going to want, well, we need an add, remove, contains, get count, is empty, size, this whole iterator thing. But of course, it's an array index bag, so we also want like special adds where if you add where you specify an index, we want to add that thing to that index. And of course, we'll have to make room for it. Remove, well, remove something at a specific index, set something at a specific index to something else, get something from a specific index, and ask for the index of something. There, that's what we want to implement. Okay. Only areas presented here are the important ones, I guess. But if we go, where we got here, no, that's the wrong one. Here, array index bag. Let's start to have a look at what we've got. Got some 3 fields, 2 of which are static, I guess. One's the default capacity. One is that special, like, not found value. We create a bag, type T, and we keep track of the rear. Our constructors are our constructors. These are going to look awfully similar to the stacks, the array stack. And we've got our expand capacity, which again is going to basically be just like the array stack's expand capacity. We don't need anything fancy like we did with the queue because the front of this indexed bag is always going to be index 0. The front of the index bag is always going to be index 0. You might say, well, why don't we do something like we did with the queue? And you're not wrong for thinking that. However, we're not really going to get a lot of value out of the idea of moving where the front is, because with a bag, the idea isn't that we're expected to be removing from the front all the time. The idea with this indexed bag is that we're retrieving information from who the hell knows where inside this thing. So when we're removing from the front a lot, it makes sense to update where the front is. But if we're removing from anywhere inside there, we can't really keep track of, like if we introduce a hole by removing something from the center of that array, we're going to want to fill that gap. Well, you haven't memorized the URLs? Right, so there's our expand capacity. And now I've got a couple other private methods. I've got the shift left, shift right, sentinel index of, and then it looks like after that it's just a bunch of the publics. Okay, let's go look at these private methods. Shift left. Well, the header here explains it all. Like shifts elements in the array down towards index 0 towards the starting index specified. This method assumes that the calling function manages the rear field. So the whole point of this is, if I've got a gap that starts at index, or if I introduced a gap at index 4, I want to be able to say, okay, shift left to move everything down 1 in the array such that index 4 gets filled. So like, look, right? So we say from start, I starts at the start, so if that's index 4, I is less than rear minus 1, and this rear minus 1 is important. We'll come back to this. But what's going on here? Well, we say bag at index I, put what's in bag at index I plus 1. So basically, hey, take what's in the next index and put it inside me. And then repeat, 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 repeat. And then once we're done, we set the last thing to null. The reason we need this minus 1 is because we've got this plus 1, right? Because if we go all the way to rear, and then we say, okay, rear plus 1, well, that's out of bounds, right? We're in trouble. So that's why we have the rear minus 1, just because we're doing this like I and I plus 1. It's common to see this pattern here when you're doing something with I and I plus 1, and then the loop's only going to like the end minus 1. And if that's not clear, let's see if I can make it a little more clear. If I have some array 0, 1, 2, 3, 4, 5. Rear is 5, let's say. All right. If I go from 0 to 4, let's see what happens. Well, I will take the thing from I plus 1, 1, and move it to 0. Take the thing from I plus 2, okay. There we go. This is where we want to stop. But if we go to where I is 4, I say, okay, then go inside what's in 4 plus 1, which is 5. But 5 is actually like empty right now because it's the rear, right? It's the next available open spot. So that's why we need to do the minus 1. Because we start at 0, and then we copy the thing from the next one over. Then we go to 1, copy the thing from the next one over. Go to 2, copy the thing from the next one over. Go to 3, copy the thing from the next one over. If we go to 4, we're going to copy the thing from 5, which doesn't exist, and move it into 4. It's not quite right. And you might say, oh, well, if it's null, then don't we want to move the null down? Well, okay, sure, fine. But what if our rear is 6? Then we'll have an array index out of bounds. So that's why we are careful with that. So shift left just basically says shift everything in the array down towards 0, starting at the index we specify. So this is going to be really handy if we remove anything and then we need to fill the gap. This private method will take care of it. But tell me, what is the computational complexity of this method right here? N. It's not 1, it's N. And the reason it's N is because, well, we always like to think of the worst case scenario, and if the start is 0 and we're going all the way to the rear, well, that's N, right? We got to put our finger on all things in that list, or in that array, pardon me. So yeah, it's N, not linear, or it's linear, not constant. And then similarly with shift right, it's the same idea here, but now this is to make room. So with the shift left, that was to close a gap. Shift right is to open up a gap, and this would be helpful for when trying to insert into a specific index. And how does this work? Well, instead we start at the rear and work our way down towards the start, decreasing I, and then we just keep moving everything from I minus 1 to I minus 1 to I, and so on and so on and so on and so on, until we get to the start, and then we set that to the null. So that means that bag at whatever that index, that's where we're going to be inserting something. So these are helper methods. This is a helper method to help with adding at a specific index, and this is helper method for removing at a specific index. Cool. And do we have any other? Right, and then sentinel index of. Search index 0. This is just a fancy way of looping through the thing. Look at each thing. This could be replaced with a for loop. Okay? But put your finger on each thing. If it's the thing we're looking for, return the index. If we ever get to the end and we don't find it, we return -1. So you might be wondering, what's sentinel? Well, sentinel is a word we used to be like, well, what do we do if it doesn't find something, right? Well, okay, I'll return a special value that means something in this scenario, and that would be the -1. So that is a sentinel value in this case. And this is a private method that's going to be used to help us out with other various methods. Any question about these 3 private methods? I mean, we've seen expand capacity, but I've got the shift left, shift right, and sentinel index of. Any questions about those? What is for? Okay, so this right here, that's what you mean? Is that right? Yeah, that's what it is. So this is making use of the iterators, which we haven't learned about yet, but this is a fancy way to make use of the iterators. What this basically says is take each element from this thing. And this thing is kind of, it's like the array called beg. We are covering this later, not right now. So if you're looking at this and you're thinking, what the hell? Here's what we could replace this with a regular old for loop or just a while loop or something as well. But I was being fancy and making use of an iterator, which we will revisit once we look at, what is it, topic. So the next one, array, yeah, the next topic is iterators. So your head's in the right place for asking, is it Python like for C in lit? Yeah, it is. It totally is. It's just here it's for bag element in, and then you specify like the collection, except here the collection is itself, which is weird, but you can do fors like this elsewhere. Let me show you. Lecture stuff. Lecture. If I just have a int array, my array equals a new int array of size 100. I don't know, why not? So I can iterate over all this, right? With for I is less than my array dot length, and I can print out my array at index I. Great. This will work, right? There's nothing wrong with this, but it'll actually allow us to do something slightly different. I'm gonna rename it to give it a more appropriate name. So what this is saying is for each value in my array, which is gonna be similar to what you're used to in Python, where you say for C in some list or something, right? Where that would be like for each thing in the for each thing that will refer to C in the list. Well, it's the same idea here, just the syntax is a little different. Here the value is C, in is the colon, and then some list, my array, this is the collection. I mean, the big difference here is because, you know, Java cares about the types a lot. So we have to say, okay, well, integer value. But if we got rid of this and then replace this with in, this should look a hell of a lot like the Python one. Yes, good observation. All right, back to the other. So here is our index of, and yeah, so this is just a fancy way of iterating over the collection. But here, remember, this is a reference to the class, like an instance of this class itself. So it's weird to look at this, but it'll make sense later. Any other questions about those private methods? Okay. All right, then what do we have next? Okay, add. Well, the regular old add, the add where we just specify an element we want to add, that's the one that's going to mean just like append to the end, add to the end. If I don't specify an index, we'll assume that they want to use the end index. Okay? Now, I could write this such that I just add it, and it would be almost like verbatim. It would be nearly verbatim what the add would be in like the array stack. Okay? But instead, because I have another add where I specify the index I want, and I give it the element, I'm just gonna call the other add from within this add. This is similar to like constructor chaining, right? Where I say like, well, just call the constructor, except pass it the value for initial capacity, give it default capacity. It's the same idea here. Okay, add to the end. All right, well, we'll just call the general add where you get to specify the index, except we'll just specify the rear. That's all. So the general add, though, is, well, let's have a look. Public void add, it takes an index and the thing we want to add. All right, well, first thing I ask is if index is greater than the size, well, we'll throw an exception. Index out of bounds exception. Bag has no index to add to. Having an exception, if you're trying to add to an index that doesn't exist, throw an exception. Seems reasonable, right? Then we say like, okay, is size equal to the bag length? If it is, expand capacity. Great. So now though, the issue is I've specified an index that I want to insert something into. The issue though is, there's something already there probably. If it's not at the end, there's something already in that index. So I need to make room. So that's what shift right does here. Shift right from that index, that'll open up the index, the cell at index for the new element. Put that element in there, and then increase rear. That's it. If you're wrapping your head around this, chances are you're thinking too hard. The first thing, if it's array index out of bounds, throw an exception. If we're out of room in our array, expand capacity. Otherwise, make room. And let's draw making room. Come on. Here. If I have like a bunch of things in here, A, B, C, D, and I want to add here, well, what I got to do is I say, okay, well, let's shift right U, shift right U. Great. Now I've got the gap and I can put the new thing in there. So I'm happy to put in, I don't know, the new thing. That's supposed to be a happy face. Let's fix that. Sure. So there we are. It's going to start calling, I'm going to start calling my add methods head and shoulders, I think. 3 and 1. What? Can someone explain that to me? Because I'm not sure. Because we've got these... What? I don't get it. Can you explain, or am I missing something? It's got the stuff for the add method, expand capacity, and now shift right. Okay, you're right. Okay, I gotcha. All right, I gotcha. All right. So that's the add. Let's do a set. Well, set's going to be easy because the idea with set is I'm going to specify an index. If the index is out of bounds, we throw the exception. Otherwise, we just go to the index at that bag location and put that element there. And you're going to say to yourself, yeah, but we didn't make room for it. But that's fine because set, we're not adding something new. We are modifying what's already in there. It's like we're setting the thing at that index to a different value. Presumably, we want to overwrite what was in there because we just don't care. Yeah. So there's our set. Get, same thing. But even simpler. It's just, if we're out of bounds, throw an exception. Otherwise, return bag at the specified index. Great. Remove. Now this is going to be a complex one because we have a remove from a specific index, and then we also have a remove where we provide an element we want to remove. So we actually have two different types of removes. The first remove is remove the thing at index I specify. The other remove is remove the thing that's equivalent to the element I'm passing to you. So let's look at the first remove. All right, if index is out of bounds, throw an exception. Otherwise, remove is we're going to get the thing we want that we're removing. So get the thing at bag index, and we save it into return element. We shift left, decrease rear, return the element. So the idea now is if I'm removing the happy face, okay, great. You're removed. I'm storing you later to be returned. Now I have to shift left. So we move you back down and we move you back down. And now I'm happy to return this and I can decrease where rear is. Of course, ignore this because that's not relevant to what we're talking about. So that's the idea there, is the remove is, if it doesn't exist, throw an exception. Otherwise, get the thing, shift left, decrease rear, return the element. Then though, let's look at the other remove where we specify an element. So it's actually kind of neat. I say, wait a second, index of. public. Ah, yes. So we've got this remove here that makes use of a method index of. So let's look at index of. This is not to be confused with sentinel index of. So the public index of says, here's the thing I'm looking for. Call the sentinel index of. The sentinel index of is just doing the linear search, and it gives me back the index of the element I'm looking for. But remember, it also returned a special value, that sentinel, if it doesn't find it. So I say, okay, well, if the index I got back was not found, I'm going to throw an exception that says no such element exception. So this would mean someone's trying to find the index of something that doesn't exist. So we throw an exception. If it is found, then just return the index. So this index of makes use of the private index of. You might be saying, how am I going to know if I should be using the sentinel one or the not sentinel one or this, that, or the other? There's no written rules here that the way I wrote this is that it's the right way to write it. We're at the stage now where there are so many valid, correct, similarly good implementations of this class that there is nothing saying that the way I'm doing it here is the correct way. So if you're saying like, oh, how would I know to do the sentinel? I don't know. You wouldn't necessarily need to know because you could write it an entirely different way. But one thing I will say is never be afraid to add these private helper methods, because the sentinel index of ends up making my life a little easier. The shift right makes my life a little easier. Shift left makes my life a little easier. Because you might say, well, your shift left and shift right, those only matter for your adds and your remove. And you're not wrong, but look how much more bite size this function is. Okay, check index out of bounds. Do we need to expand capacity? Make room, add it, increment rear. There's nothing wrong with me doing this. I could say, I could copy this, I could paste this here, and it'll work just the same. I guess start won't matter here. Start would be index. But I don't know. To me, this is a little uglier. It's not wrong to do it without the private helper method, but I don't know. The private helper method, I look at the shift right, I know what that is. So they are functionally equivalent, but I would argue that this implementation I have here, making use of this private helper method called shift right, is, I don't know, it's a little more readable. It's more explainable. And readable, understandable code is very important. It's not just about being correct. It's about being, like, understood. And you don't need to do this private method. But if you think having a private method or an extra method would be helpful for your classes or any other code you're writing, do it. Unless you're explicitly told no extra methods, which would be a weird thing to say, do it if it helps you. Highly recommend it. A lot of students at this stage tend to get a little worried, like, oh, should I add a private method here? Sure, your call, up to you. If you start writing it and realize you don't need it, whatever, fine, delete it, doesn't matter. If you start writing it and you realize you need 3 others, cool, write those 2. It's up to you, doesn't really matter. So we've got our get, our remove. So now let's look at the remove after learning about the public index of. That makes use of the sentinel index of. So we call index of. Index of will throw an exception if we don't find what we're looking for, which is what we would want. We would effectively say, like, okay, removing from an empty bag. Well, that's what happens if we try to remove when it's empty. But what happens if we try to remove something that doesn't exist? Well, we throw the exception, no such element exception, because we are just calling this method right here. Presumably then, well, not presumably, if we get the index back and it, meaning index of, didn't throw an exception, then we know the index that I got is the index of the thing I want to remove. So then I just call the remove on index, which is this remove that we just looked at. So the remove where you specify the element you want to remove just hijacks the other remove. all this is doing is saying, okay, remove a specific element. Okay, well, do a linear search for that element and then remove it at that index. And removing at that index, we already wrote that, which is kind of handy, right? Any questions about these two? The remove and the other remove? And you might get a sense that, like, yeah, okay, by making use of other methods and private methods, you can kind of see how, like, look how nice and simple these methods look. That, when I say simple, I don't mean trivial. I mean, like, they're, like, concise. They're succinct in what they're doing because I'm able to make use of other methods that are solving problems for me because we love abstraction. I heard a boop. Do you have a private method to do the linear search? Yes, that's my sentinel index of. That's this one right here. So index of hijacks sentinel index of, and this is just the linear search. If we ever find what we're looking for, we return the index. If we ever get to the end and never find it, we return not found, which is just -1. Why are you talking about sliders and burgers? It feels off topic. Bit-sized. Bite-sized. Okay, what? Why are you talking about that? You could have at least made a computer joke and call it BYTE. Come on, guys. All right, get the thing at a specific index. Oh, wait, we already looked at that. Remove index of contains. Perfect. Let's look at contains. Contains just is returning true or false if a target exists. So I'll just say, okay, find that target. Sentinel index of. If you're not found, return true. If you are not, you know, like, so this just tells me, like, basically if the result of this is not found. Get count. So this is just a linear search here. Count is 0. Do a linear search over the bag. If I find the thing I'm looking for, add to the count. When I get to the end, return the count. Is empty is size equals 0. Size, return rear. Iterator is now this thing we're seeing called an array iterator. And then we've got our toString. So remember, we are getting to the iterator. That's the next topic. But it exists. Just be aware of that. We'll talk about it, not today probably, but on Tuesday. And we've got our toString, because we always like toString. So we say, we'll use a string builder because that's the right way to do it. We make use of the iterator basically for each bag element, append it to the builder, and then append it with a comma space. Repeat, 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 repeat. Then say, builder, give me your string, and return that. That's all. And that's it for the array indexed bag. I'm willing to bet when you first looked at the idea of the array indexed bag or the indexed bag, it feels intimidating because, wow, there's that much more functionality and stuff we need to keep track of compared to your stacks and your queues. And that's absolutely true, but I don't know. I feel like we're able to make that step towards this additional level of complexity. Because the added complexity was kind of solved with these private methods, the shift left, shift right, because that's the issue, is making room, and because we can add and remove from any arbitrary spot. So it's just more of an issue of making room for those things. That's it. It all looks intimidating at first. Yeah, yeah, I get that, yeah. But then you practice and then you do it. By the way, I entered the midterm grades. The median grade in the class is like 90. I realize that those numbers are skewed because it only includes your assignment 1 and your labs. And if you show up to labs, you got perfect. And your assignment 1 is worth 15%. So, and that's perhaps the easy one. But point is, y'all are crushing it so far. So keep up the good work. No, midterm grade, no, not the test. Yeah, I hate that they call it mid-semester grade. Is that better? Yeah, okay, cool. All right, so that's it for the array index bag. So let's see, was there anything in here not found? Yeah, private methods, okay, yeah. Expand, yeah. Iterator. Iterators are focused on the next topic, so we'll only present them briefly here. Okay, we made use of the method and other methods calling this dot iterator. In fact, it was even more. These are the commented out examples. If you're wondering, hey, why is there this weird copied out version of Sentinel index of? It's because it's using a slightly different type of iterator. You'll see. We're going to learn it all. Which calls the method iterator from this class. This is what we do. All this method does is create an instance of an array iterator and returns it. We will look at array iterator class. We will look at what the array iterator class looks like in the next topic. An iterator, briefly right now, you can think of an iterator as a stupid little robot that starts at the beginning, or wherever you specify, but let's, for simplicity, we start at the beginning of our array, and we put our finger on each thing in some specified order. With a linear collection like an array or this bag, there is only one order. The thing at the beginning, then the next thing, then the next thing, then the next thing, then the next thing. This little iterator is a little robot that moves down the line and goes, okay, you. And it's used to loop through the things in a consistent way. And let me see if I've got a good example here. Let's see, array queue. Yes, okay. And now linked queue. What? Do I not? Oh. Okay, the toString. So, look at how we've got this array queue toString and the linked queue toString. Because the array queue makes use of an array, it makes sense to make use of the for loop that starts at 0 and goes to size, right? But a linked queue, you know, we can't really use the for loop. I mean, we totally could use the for loop, but it's just as easy to use a while loop saying, well, the current node is not null, and then, you know, you move down that linked structure. But you know what's kind of annoying is, I don't know, the code from here and the code from here are nearly identical. The only difference is like, this is a for loop, this is a while loop. Yeah. And that's basically it. So it's kind of annoying. Wouldn't it be great if there was a way to write a loop such that it didn't matter what the underlying container is, whether it's an array or a link structure, but if you could loop over it in a consistent way? That's where iterators come in. That's all. Okay, there's link queue, array sorted bag, topic, array index bag. All right, next is the array sorted bag. Okay, add methods. Let me make sure I'm not missing anything big here. Index of array sorted. Okay, good. So the reason I just skipped over all this is because we just went over it by looking at the code. So now let's look at the array sorted bag. The array sorted bag needs to be everything a bag is, but you know, our add needs to work such that it inserts the thing at the correct location, right? Because it's a sorted bag. If I want to insert 55, 55 better come after the number 50, but before the number 70. It should go before the number 50 because then it wouldn't be a sorted bag. So add needs to work a specific way. And we also want to remove first and a remove last. And a first and a last, which is kind of like your peak and your front with the queue. These actually remove it. These only return a reference to it, but keep them in the sorted bag. But these are the key things we're going to want here. So let's go look at array sorted bag. And by the way, array index bag. Look at the top here. Oh wait, no, this one's not even that bad. Okay, yeah. So there is a lot going on in this class declaration. Look at this. Public class array sorted bag of type T extends comparable, which is question mark super T that implements a sorted bag. What the hell does all that mean? Okay. It actually is far simpler than it seems at first. let's start by let's pretend this part wasn't there. If that part wasn't there, you're used to this. Public class array sorted bag of type T implement sorted bag type T. Right? We're happy with this. And this is the same as the array index bag. Just see, it's the same. But where it gets different is where I've got this extra T extends comparable question mark super T. What this is saying is, all right, I'll leave it, I'll get rid of this here. And I'll add to that in a second. T, okay, the thing that we want in our sorted bag needs to extend comparable. And we can actually just do this for now for ease. It needs to be comparable. What this is saying is the things of type T that we want to add to the sorted bag need to have some sort of ordering. Otherwise, you can't add them to a sorted bag. Does this make sense? If I say, add the number 55, and then add the number 66, and then add the number 22, and I say, well, what order do those things go in? If you compare them, you go, well, 22, 55, 66. Why? Because that's the order that numbers are. We've been used to number order since we were this big, right? But the trouble is, if I say, hey, add this, remember at the beginning of the semester we had friend objects, right? If I say, add friend A, friend B, and friend C to this array sorted bag, you might be asking the question, but what's the order, right? Like how, you're telling me to add these things. How do you want me to, like how do I order them? This is a sorted bag. Are they ordered by height? Are they ordered by first name initial, last name initial? Are they sorted by age? I don't know. So what this is saying is, whatever the type T is, so type T means anything. But when I say type T extends comparable, that means the thing, it's generic, and T can be anything as long as it's comparable, as long as it makes sense to have these things being ordered. We have not, at this stage, we have not written any classes that extended comparable. Okay? But this is saying, oh, the thing of type T that we're adding better extend comparable. Well, the good news is things like your integers extend comparable already for you. But it's really easy to write code, or it's really easy to write a class that defines comparable. Real quick here, if I go, here, I'm going to go to the other lecture stuff. Friend. So here's the friend class from like the very beginning of the semester. I'm going to say extends comparable. Why is this not happy? Oh, because I'm not implementing that. No, implement. Does it need to implement or extend? Implement methods. There we go. Compare to. There we go. So if I'm saying, oh, I'm extending comparable, I need to implement compare to. That describes, well, how do you compare to friend objects? What comes before what? What's equivalent? So we write these compare tos. In assignment 4, you will be doing something very, very, very similar with something called a comparator, which allows for slightly more sophisticated comparison rules. But that's what comparable is. Long story short, you want a bag of type T? You want a sorted bag of type T? Well, the things that you want in the sorted bag better be sortable. That's what the comparable is here. Okay? Yeah? Any questions about comparable? So, The only other thing was this weird question mark super. Is this deals with inheritance. I really don't care what the class is. Wait, hold on. Let me make sure I say this right. And even then I might get it backwards. All that really matters is that one of the parent classes. It's not even that the thing of type T needs to extend comparable. It's that really T or one of its parent classes, one of its super classes, must extend comparable. Because remember, if I'm inheriting, if my parent class has the comparable defined for it, then I don't need to redefine it if I don't need to redefine it. Sure, I might want to override it, but if one of my parents is comparable, then it is. I would not expect you to memorize this. That's kind of nasty. This is one of those things where you sit down and you go, okay, what do I need? And you start typing it in, and then the IDE will be mad at you. Be like, well, if you want it to be comparable, you need to make sure that your thing of type T extends comparable. Like, the IDE will help you here. I would never remember this off the top of my head. So just be warned. I explained what this is, but it's not like this is something that it's like, oh my God, this is on the test. I better memorize how this all this means is, sure, we've got a sorted bag of type T, but the thing of type T better be comparable. In fact, you would think that maybe sorted bag, does sorted bag actually... No, it doesn't. Probably should, but whatever. So yeah, there. The thing of type T, it's sortable. So if you want to add this thing to the sorted list, that's something that makes sense logically. Does that make sense? Because if you're defining a class, so remember how like we were defining a class where it's like, well, what does it mean for two friend objects to be considered equal? And you're like, well, I don't know. And it's like, well, you have to kind of come up with that, right? Because you defined this friend object. So what would it mean for two friends to be equal? Then you actually had to write the code to tell Java, this is what it means for friends to be equal. Great. But now if the question is like, well, how do you compare friends? How would you like, what comes before who? Well, you got to tell Java somehow. And that's where the compare to comes in. You're being really quiet. I can't tell if it's because you're all really happy with everything or if it's because you're freaking out. I'm going to assume you're all happy, but let me know if you're freaking out. Okay. Our constructors. Oh, I hear a boop. Probably both. All of the above. Okay. The constructors, these are the same as the index bag. Expand capacity, same as the other. We've got our shift left, our shift right, our sentinel index of. These are all going to come in handy. But now I also have another private method called find insert index. So the question I have to figure out is, I want to add this element. Okay? And this element of type T extends comparable. Why? Because I'm saying it must by this. So this thing of type T element is comparable. Meaning that if I want to compare elements, I make use of the method called compare to. Similarly, if you wanted to check if they were equal, you would say element.equals bag element. But I don't want to check if they're equal. I want to check, well, who comes first? And the way compare to works is like it returns a negative number if this comes before this. It returns 0 if they are equal. And it returns a positive number if this comes after this. So what I am saying here is if the element is... Hold on. If that's less than or equal... Maybe it means... Maybe I'm getting this backwards. Hold on. If the current bag element is, maybe I said it backwards before about the order of the negative and the positives. Point is, this is going to do a linear search to tell me where the bag element goes. It goes through and it'll keep looping until this isn't the case. Or sorry, until that's the case. All right. Sheesh. Can you tell it's Friday? Let me get my head on straight. So this is going to loop over each element. And as soon as the element I have is less than hold on. As soon as the element I have is less than, no, but it would have to be bigger than. Man, you can tell my brain's not firing on all cylinders. This might be a good place to end today. What it does do is a linear search to tell me where the search index is, like where I want to insert something. So this is going to loop until it finds the spot where this element goes based on the ordering of those elements. This would be like saying 55. Does 55 go here? Well, the thing there is the number 7. Okay, no. So you keep looping until, I guess, big element. Yeah, I'll have to, we're definitely going to pick back up here on Tuesday because my head's not working right. But that's the private method. We'll revisit this. Our add, all right, if we're out of room, expand capacity. Otherwise, find where we need to insert. Shift things to the right. Add the thing to that index, increment rear. Remove first, all right, well, just remove the thing at index 0. Shift left all the way to 0. Rear, minus, minus, return the element. Remove last, same idea, just the other end. Remove a specific element. If it's empty, throw the exception. If it doesn't exist, throw an exception. Otherwise, get the thing from that index that we just found for the element we're searching for. Shift left to the index we removed from, decrease rear, return the element. First, last, contains, it's the same as the index one, just call sentinel index of and check its equality with not found. Count, same thing, loop over, count every occurrence with equals. Is empty, size, iterator, toString. There. So none of these should be overly crazy. Sure, there are new ideas incorporated, but based on how it was written, these are all designed to be bite-sized. The worst thing here is this, is find insert index. So, why can't I wrap my head around this right now? You ever get so tired and like your brain's not working enough that like you are aware, you're like stepping outside yourself and you're like, why am I so bad at this right now? That's happening to me right now. Oh. Yes, you all know what I mean. So, as soon as the element is bigger than, so I guess this would loop until the element is bigger or equal to the bag element. So if the thing I want to insert, no, it would have to be, yeah, as soon as the element is bigger, yeah, I'm not even going to try right now because now I'm just going to confuse myself and confuse you. We will revisit find insert index. I wouldn't be surprised if 2/3 of you right now are like, why is he having such a hard time with this? That makes perfect sense. Yeah, I don't know. I'm tired. We'll wrap up here for the day and we'll pick up here on Tuesday. But also on Tuesday, with the exception of going over that one private method, we will jump into iterators and we'll learn how they work. And they're pretty cool. So what's kind of neat though, I'll just take a moment to say I realize we're basically at time. Here's where we currently are in the course. We're basically done the bags. Then we're going to learn about iterators and exceptions. And then these are kind of like, oh, hey, by the way. Exceptions you're already familiar with. Iterators you're kind of familiar with whether you like it or not. Memory and the call stack, maybe a little familiar with. But then it's recursion, searching, and then trees. Like we are on a roll. Keep up the good work, everybody. Anyways, have a great weekend. Try to relax. Do you think we know enough to do assignment 4? As of now, no, that'd be pushing it. Assignment 4, you'd be good once you hit like trees, maybe binary trees. Assignment 3, you're definitely good for now. But assignment 4, you're going to want until we get to the trees. I mean, you could probably still do it, but it'll probably help if you have the trees. Anyways, I'm going to stop recording.